question one. Question one is your rate in, rate out question. It is on the calculator here. So it gives you people entering the line for the escalator at this rate. So there's your rate in. And then it says that people exit the line at a constant rate of 0.7 people per second. So that is your, that is basically your rate out. And since the rate out is a constant, it's just going to be that 0.7. That is going to be the rate out. So part A says how many people enter the line during the time interval from 0 to 300. So since it's asking during the 0 to 300, we don't need to factor in the initial condition, but I did write it down over here. Anytime it gives you a starting amount or a starting point, it's always a good idea to highlight it or write it down or wherever. And it's just talking about entering the line, which means we're only using the rate in function. So from 0 to 300 of the function, type it in your calculator, and you're going to get 270. That's your answer for part A. Part B says how many people are in line. So don't forget that this is using an integral, because these are the rates that we are entering and exiting the line. So if we want to know how many people are in line, we need to know the integral to do that. And it gave you a clue that you should be talking about the integral and not the original function, because it says there are always people in line. So you don't just want to plug in 300, which is what I saw a lot of people do. You want to actually do the integral. And this time, since we want to know how many people are in line, we need to factor in how many people there were in line to start with. So this time we are using that 20, and then the integral from 0 to 300 of the rate in minus the rate out. Rate in minus the rate out, so that we know we're factoring in how many people got in line and also how many people exited the line. So basically, there's a net change of 60 from the time interval from 0 to 300. So instead of 20 people in line, now there's 80 people. For greater than 300, in which the rate in is 0, so there's no one getting in line. What is the first time that there are no people in line for the escalator? So since there are 80 people in line at 300, then there's only the rate out, which antiderivative would be negative 0.7 t. Then we want to know when this is 0, and solve that. You get this number, and that's the number of seconds after 300 that there are no people in line. So that final answer is the 414.2857. And then part D asks, what time is the number of people in line at a minimum? To the nearest whole number, find a number of people in line at that time. So in other words, if we're trying to find a minimum between 0 and 300 for the number of people in line, then anytime we want a minimum, that's going to be take your derivative, find where it's 0, make a sign chart. Well, the derivative for the number of people in line, the function for the number of people in line is that integral we had in part B. This is my function for the number of people in line. So the derivative of that is just my rates that I'm given. So the derivative for number of people in line is the rate in minus the rate out. So we're going to find where that is 0 and change the sign from positive to negative. So that function in the calculator and try to plug in your points. Equals 0 and changes from negative to positive. So my candidate for the minimum from there is the 33.01. So it's between that and my endpoints. And luckily, we already know the endpoints. At t equals 0, there's 20 people in line. We were given that. And at t equals 300, there were 80 people in line. We found that in part B. And at t equals 33.013258, then let's plug that in. And we get out 3.8034, which is smaller than 20. So there's where our minimum is. So remember, anytime you're being asked for a maximum or a minimum, then you want to be thinking about where the derivative is 0 and changes signs. And since it's a closed interval, we want to be thinking about the endpoints. Question 2, here's your particle question. Particle moves along the x-axis. There's my velocity function. And then again, we're given an initial condition that the position is -5 at x equals 0, or at t equals 0. So we're going to eventually use that. Part A says, find the acceleration at 3. And so if I've got velocity in front of me and I want acceleration, then I want the derivative at that point. So I'm going to take the derivative, plug in 3, and get my answer. Done. This is part of what I meant when I wrote on quite a few of your papers, use the calculator, because some of you were trying to do this derivative, these parts of the derivative by hand here on part A. Don't do that to yourself. It's going to be math 8 for n derive. It's how to do that in the calculator if you don't know. And then type out the function, and then it's going to ask for x equals what, and it's going to be at x equals 3 since we're plugging in at 3. So math 8 for derivatives on the calculator, math 9 for integrals. Speaking of integrals, part B asks for position. So since we want the position at 3 and we have the velocity in front of us, the velocity is going to have is going to need an integral to get back to position. So I want the integral from 0 to 3 of the velocity, and I need to factor in that starting point of -5. So we started at -5. Here's how far we moved between 0 and 3 from that -5, which winds us up at the -1.76. Evaluate the integral from 0 to 3.5 of v of t and of the absolute value of v of t, which are just, get them out of the calculator. Right? They tell you exactly what to put in the calculator, so put it in the calculator and get out what they are. And then interpret the meaning in the context of the problem. Make sure you're including the context of the problem. So that means to talk about the particle and give what the bounds are. So don't just say, you don't need quite this much, but you do need to say total distance traveled. You do need to talk about from 0 to 3.5. And if there were units, you should include units. And you should know that the integral of absolute value velocity is total distance traveled. The integral of just velocity is the net distance. In other words, it's saying here's how far to the right or left of the starting place I am when I get to 3.5. And then integral of absolute value of velocity is total distance traveled. Part D. A second particle moves along the x-axis with the position given by t squared minus t. Well, that means if we want to know when the two particles are moving with the same velocity, that means we need the velocity there, because t squared minus t is not my velocity. I need to take the derivative. So my question is, when does the derivative of that position function I just gave you equal my velocity function? Well, the derivative of that position function is just 2t minus 1. So we're going to set that equal to the velocity graph in our calculator. So graph 2t minus 1 in one of your graphs, graph that velocity function in your other graph, and then figure out where their intersection points are between 0 and 3.5. And that point is going to be at 1.57. So again, we have the velocity of one of them. We take the derivative of the position function they gave us to get the velocity of the other one, and we're just going to set them equal to each other and solve, which our calculator is going to do for us. A lot of work that your calculator can just do for you on this question. Make sure you know how to use it, and don't try and do a whole bunch of messy derivatives by hand when you have a calculator in front of you. Question 3, we practiced quite a few of these questions, but this one was pretty tricky because it expected you to work with the piecewise function here. So again, we're given this, this graph. And it's saying that the function is piecewise linear from -5 to 3. So from -5 to 3, we're basically using segments. And when we do integrals, we're just going to use area formulas. When we do derivatives, we're just going to use slopes. Then from 3 to 6, we're using this parabola. And so that might require you to do some antiderivative work or something like that. So if f of 1 equals 3, what is the value of f of -5? So this is giving you the f of 1 equaling 3 is giving you the starting amount. And then you want to know the value of f of -5. Well, then that is the integral from 1 to -5, because I'm going to put -5 in for the integral, because since f prime is g, then that means that the integral of g, the integral of this graph that's in front of you, is going to be f. So if I want f at 5, I want the integral starting at 1 and ending at -5, which I'm going to switch my bounds and make this a subtraction. And so to get the integral from -5 out to 1, then that involves taking some areas of some rectangles and triangles. And so that's what you see me doing here. Remember, if the area is below the curve, I'm counting it as a negative. So I'm accumulating out all that area, and then we're going to subtract all that out, and I get 25 over 2. So finding f of -5 involves using an integral of that graph, which if I have a graph in front of me, that means we are talking areas. That's part A. Part B, evaluate the integral from 1 to 6. Well, the integral from 1 to 6 is a split in my piecewise function, because the piecewise function is split at 3. At 3, the function changes. So that means when I talk about the integral should be split at 3. From 1 to 3, we're looking at a bunch of straight line segments, and to get the integral, we're going to talk area. From 3 to 6, the function is this 2 times x minus 4 quantity squared. So from 1 to 3, there's my area. And then from 3 to 6, antiderivative of this is going to be 2/3 times the quantity cubed. And so plug in 6 minus plug in 3. To get our total answer there. Part C, when is the graph of f both increasing and concave up? Again, I'll talk about point values in a second, but you should put your explanations and reasoning here in terms of the graph of G. Whatever graph or whatever function they give you is the function that you should put your explanation in terms of. So for this question, when it says when is f increasing and concave up, well, G is the derivative of f. So the function is increasing and concave up. Well, it's increasing when the derivative is positive, when it's concave up when the first derivative is increasing, so that the second derivative is positive. So f is increasing and concave up when G, which we know is f prime, is positive and increasing. And I always get in the habit of writing those explanations first, and then once I have those explanations, looking at the graph and saying, when are we above the x-axis and going up? And that's from 0 to 1 and from 4 to 6. Part D, same thing. Explain it in terms of f, or in terms of G, in terms of the graph in front of you. So the first derivative of f. So we have a point of inflection when the first derivative, well, it's when the second derivative equals 0 and changes sign, which is when the first derivative has a maximum or a minimum. Or when that first derivative changes from decreasing to increasing, so that the second derivative will change from positive to negative or negative to positive. So x equals 4 is our inflection point there. So some pretty complicated stuff on A and B, I would say, but hopefully C and D felt doable. So make sure we don't, give up on a question just because part A is hard. Part A is the hardest part of this question, in my opinion, and then it gets easier from there. Question 4. Here's our table. If we're estimating h prime of 6, we're going to estimate h prime of 6 by using the slope formula, because derivative measures slope. That's what they're trying to get at with asking this question. So to estimate the slope at 6, let's take the slope formula using points around 6, which would be 5 and 7. So we're going to take slope at 7 minus slope at 5 over 7 minus 5 and get 5/2. Part B is a mean value theorem question. We want to know if the derivative at any point is true. So we want to know if f of b minus f of a over b minus a at any point in this interval ends up being 2. Oh, sorry. On part A, they also wanted you to explain. It said using correct units. So one of the things you need is the units of meters per year to make sure that you are getting that. You want to talk about what the 6 means. You want to talk about what the h prime means, which is the rate of the function they gave you. So the rate of the height. Then for part B, mean value theorem. And our sweet spot of our f of b minus f of a over b minus a is h of 5 minus h of 3 over 5 minus 3 ends up being 2. And so between that 3 and 5, and so by extension between 2 and 10, more specifically between 3 and 5, h prime has to be 2 somewhere in that interval. That's a mean value theorem question. Part C, average height with a trapezoidal rule. Since the intervals are different, you just need to think about it as an area of a trapezoid for each of the values on the table. And then the other thing that needs to happen is that this 1/8 needs to be out in front. Why is there 1/8 out in front? Because it's asking about the average height of the tree. So average value of the function is 1 over b minus a times the integral from a to b. So you want to make sure that that's the integral you're estimating. So 1/8 constantly out in front of these values. And then I'm showing 1/2 the height times base 1 plus base 2 for each component, for each piece. Add them all together. Do some adding together of fractions, and that's our answer. And meters is going to be our units because this is asking for average height. So this is a height question, units in meters. And then part D, I said not to worry about. We haven't done it yet. We'll do it next week. Number 5, here was our function, e to the x cosine of x. And we're going to be looking for average rate of change. Average rate of change, don't forget, is not the same as average value. Average value was the 1 over b minus a times the integral from a to b. But average rate of change ends up being f of b minus f of a over b minus a. So don't try and work with the integral here. We actually didn't learn how to take the antiderivative of this. That's a Calc BC topic. So you will not need to take the integral of this. It's just using derivatives. So average rate of change is f of b minus f of a over b minus a. So f of pi minus f of 0 over pi minus 0. So plug that in, get out your answer. Part B asks, what is the slope of the line tangent to the graph? I talked a lot about this as we were studying for the final and first semester. As soon as you see slope of the line tangent to the graph at a point, or slope of tangent line, then you should be thinking derivative. This is, part B is another way of asking, what is the derivative at 3 pi over 2? So that means we need to take the derivative, plug in 3 pi over 2. So the derivative here is a product rule, and I'm going to go ahead and factor the e to the x out. And then I'm going to plug in 3 pi over 2. And it is e to the 3 pi over 2 times, and when I evaluate these cosines and sines, it ends up just being 1. So it just ends up being e to the 3 pi over 2. Absolute minimum. This is part C. Absolute minimum. We want to know, I have the derivative in front of me. We want to know when this changes, since minimum, we want to know when this changes from negative to positive. We also need to factor in the endpoints since we're on a closed interval. So that's what we're going to do. F prime is 0 when cosine equals sine. In other words, when cosine of x minus sine of x equals 0. So that's when cosine of x equals sine of x. And that happens at pi over 4 and 5 pi over 4. So let's make our sign chart and look for when we're changing from negative to positive, since we're looking for a minimum, and that's going to be at 5 pi over 4. And then double check our endpoints as well. Here's 0. Here's 5 pi over 4. I know it's not going to be 2 pi because after I hit that minimum, I increase all the way to 2 pi. So that's got to be bigger than 5 pi over 4. So it's out as my minimum. But let's check 0 just to be safe. At 0, we're at 1. And at 5 pi over 4, we're at this number, which is negative. So it's going to be smaller than 1. Part D. No one caught that part D is your L'Hopital's rule question, because it is asking for the minimum of f of x over g of x. It's asking for the limit of that, and both the top and the bottom end up being 0, which a lot of people caught. So since both of those functions are continuous and differentiable there, top is 0 and bottom is 0, so we can use L'Hopital's rule. So that's saying that the limit of top of this fraction equals the limit of the derivative of the top over derivative of the bottom. And when I do that, the derivative of pi over 2 is e to the pi over 2 times 0 minus 1. And then the derivative of g at pi over 2, well, I just look at the graph that they give me because that's the graph of g prime. This is the graph of g prime. So at pi over 2, g prime is at 2. And so 2 goes on the bottom. And that's your answer for the limit. So that one was tricky because catching that it's L'Hopital's rule was difficult. Number 6, it asked on the slope field, it asked for you to sketch the solution curve that goes through 1, 0. So this is basically your connecting the dots question. So I want it to pass through 1, 0. Well, at 0, 2. First off, at 0, 2, all the slopes are just horizontal. So at 0, 2, it should just look like a horizontal line. And then at 1, 0, we just want to connect the dots, and our curve should look something like this. So horizontal line at 2, and then this curve at 1, 0. Then it asks for equation of the tangent line at 1. So that means I need the slope when f of 1 is 0. So I'm going to plug in 1 for x and 0 for y and figure out what dy dx is. And it ends up being 4 over 3. So I need to put in the equation of the tangent line. And then it says use that tangent line to approximate at 0.7. So if I plug in 0.7 into that tangent line I just gave, then I get 4/3 of 0.7 minus 1, which is negative 0.4. So getting your equation of the tangent line and then plugging in 0.7. And we get slope of the tangent line by figuring out what the derivative is at that point. And finally, part C. Part C is a separation of variables question. So anytime it says, if it says a question like find the particular solution, when I'm given dy dx, you can look back at your homework. That's how these separation of variables questions were phrased. Quite a few of you recognize that it was separation of variables, and that helped get you some points. Here's how I did it. Separate out the variables, antiderivative, and then I plugged in the point and solved for C. And then after that, I needed to get y by itself. I went ahead and multiplied by 6 here to get rid of the fractions, so that that was easier to work with. And then did some multiplying and dividing, add 2, and there's my equation with y by itself. So that is your separation of variables question.